Alright, in this video we're going to extend what we did the other day with mechanical waves, and we're going to turn it into a special kind of wave. And there's a special one that are called standing waves, or a special kind of wave called a standing wave. And this is a wave. Remember, waves can reflect and refract, and we're going to get into all of that. But if you go outside and yell against a building, you stand a little bit of ways and you yell or you clap really loud, you hear an echo, that bounce back. That's a reflection. And this is formed when two waves with the same frequency, so they have the same number of waves per time period, and we'll get to that in just a moment, but the same frequency and amplitude in opposite directions. So I send a wave one direction, its reflection comes back at the same strength. Remember, the amplitude means the strength of the wave, and the same frequency, so it's the same number of waves per second. I'm not going to go through these definitions here because you can do this on your own. This is on your vocab list, and it was talked about in the first section, so wavelength, amplitude, and frequency. And hertz is a measure of frequency, so you're going to have to make sure you don't get the car company hertz, get like frequency, waves, hertz. But to do this one, I'm going to show a video in just a moment, but I want to look at this thing called an oscilloscope. So we've got a wave here, and now what's really cool is I turn on my microphone, and you can see the input given changes the shape of the wave on the screen. So let me do my best. I'm going to whistle for a minute. Watch the shape of the waves. And now I'm going to do a higher pitch. So notice the waves got closer together. So here's the low one. Okay, let me pause the live input. We're going to look at a sine wave. So here's a wave. Remember, a wave is a full cycle. So we go up once, down once, and back to our resting position. And it's set at 250 hertz right now. As I increase my frequency, so I get more waves per second, look at the wavelength. The wavelength. So now I've doubled more or less my frequency, and I have one full wave in about a third of the distance of the original. And I can take this all the way up, and they squish together. Notice the amplitude, the height does not change. The height change comes as we increase the input, so the strength of that wave, right? So it's just like increasing the volume. So this is how an oscilloscope works, and it helps us see. So this would be a standing wave. It's a repeating pattern of waves. So we're going to jump to the other video, and then we'll come back and we'll finish up the diagram. This is a good standing wave. We've got a nice graceful arc here that shows the curvature of the waves. So this is called the antinode, and this is where the waves are accenting one another. They're amplifying each other. And this is the fundamental frequency for this string. And here's what's called the first harmonic. So we've increased our frequency, and here's right in the middle is a node. You can see the string is staying still, and now instead of having one antinode, we have two antinodes and a node in the middle, additionally to the ones on the outside. So these two antinodes and a single node is because we've increased the frequency and the waves are interfering with each other a little bit more. Okay, so we just saw a standing wave. We looked at how it's actually generated on the wave machine. And here are some simple diagrams. Your paper, you need to sketch these in there. Remember, this is a single string oscillating back and forth. So this first standing wave, this is called the fundamental. This is where an object, a string, matter, it's a mechanical wave, so it needs matter, where it oscillates naturally. Notice we have two nodes. We'll do these in blue. We have one node on the left and one node on the right, so we have two nodes. And one antinode. This middle space here is one antinode. And in the classroom on my wave machine, I was oscillating this at 33 hertz. So it's 33 oscillations per second. And then we bounced it up to 66 hertz, more or less. And my shape changes. I have one string, but I've shortened my wavelength. This is only half a wave right here. Now I have one full wave in the same distance, so my frequency has gone up, right? We've got more nodes. We have 1, 2, 3 nodes now. And we have 2 antinodes compared to our 2 to 1. This first bump, this is called the first harmonic. So I've doubled my frequency. This is called a harmonic because I'm keeping that standing wave. And now we've got 3 nodes and 2 antinodes. So notice we have a pattern with each harmonic. So this last one is called the second harmonic. We have another antinode. Go back to blue. So we've got 1, 2, 3 antis and 1, 2, 3, 4 nodes. And this happens all the way up. You can do as many multiplications as you want. You don't need to worry about the tension, like how the tension works out, how the waves work. We're not going to get that deep with things, but this is called a standing wave. Guitars, you see this on a guitar string. You see this on a piano string when you resonate a guitar or a piano string. It's at a much higher frequency, so it's harder to demonstrate in the lab, but the principle is the same. Those strings all resonate with a given frequency. Notice these are transverse here, drawn, but longitudinal can do the same thing. That's how speakers work. That's what sound is. So when you hear a nice pure tone, that's a standing resonant wave. Thanks for taking a look. If you have questions, be sure to leave it in the comment, ask me in class. I'll see you next time.